My guest today is Stefan Thurner, a professor of theoretical physics and the president of the Complexity Science Hub in Vienna. Stefan has published over 240 scientific articles, and he was elected the Austrian Scientist of the year 2017. He is also an external professor at the Santa Fe Institute. In our conversation, we first delve into the scaling laws of everything. We explore social, financial, biological, and economic dynamics. For example, how to make the economy more resilient by targeting some unique companies, how social bubbles form, and the strength of networks of friends and foes in social contexts. We then discuss his approach to science and how the methodology of physics can help us understand all the fields. I hope you enjoy our discussion. Stefan, thank you so very much for accepting my invitation. I'm delighted to welcome you on the podcast. One issue I have is that I have way too many questions for you because your work is too relevant to the theme of the podcast. So we'll see how far we can go. But what I thought I'll be doing is to divide the conversation in two different parts. In part one, I want to talk about scaling laws and explore all of your publications. And then I want to talk more about, in part two, your approach to science, the way you see yourself, and the work you've been doing as well with the Complexity Science Hub in Vienna that you are leading. So on that, for now, exploring some of the scaling laws, I will be going through some of your publications, but maybe before even we do that, I have two general questions to start. And the first would be, what is, amongst all of the scaling laws you've encountered, what is the most robust that you found over those years?
That's a tough question because very often that when you find scaling laws, these are robust. So I wouldn't know where to start listing the most robust scaling laws that I've ever seen.
Let me then ask my second question, which is, which of the scaling laws you've encountered was the most surprising, the one you were least expecting to find?
The most surprising thing that I've encountered is that if you have systems that are driven, that are out of equilibrium, but driven, where you need an outside force to keep them going, almost all of these systems must lead or do lead to scaling laws. So that's something that's really remarkable and unexpected in the sense that this observation is so general.
Yeah. So it's a law of scaling laws.
I think so. That's as I see it today. Yeah.
That would be a good title for a book or a paper. And I think only you can write that. But we'll come back to that in just a second, because I want now to indeed jump from one field to the other. Because you've been doing that. So it's not me trying to trick you. I'm just telling that to all the listeners. And I will ask for rather brief descriptions. And to be clear, the link to all of these publications is included in the note to this episode. So if you are into it, feel free to explore that. But for now, I would like to dive into some of the scaling laws that you have encountered. And I will start with your work in it's hard to put label, but if I had to put one, I would call that sociology. And here I'm referring to one paper you have entitled Measuring Social Dynamics in a Massive Multiplayer Online Game. And so in this study, you've tracked every action of 300,000 players engaged in an open-ended game called Pardus. And you've done that over the span of 3 years. And you say you have identified two social laws within communication networks. So could you please unpack what are those laws?
Yeah. So in this game, we have practically every interaction between any two players in the game. And if you look at all of these interactions at the same time, you find these are networks. And in these networks, we found some structures that are very, very nice to find. And the final result that we got is that the weight of a link between two people in conversation or in being friends is a function of a network property that needs all the network information to be computed. And this law is by itself a scaling law.
Okay, let me explore another of your publication, which I think relies on the same data set, and that is how women organize social networks different from men. That's the title of the paper. And in this one, you tackle what you called multiplex networks, and that is the superpositions of different social networks like communication, friendships, and trade. And you show that as the networks scale, and here I quote you, females and males manage their social networks in substantially different ways. And to be more specific, you find that females show high clustering in trade and males have fewer cooperative links, with a tendency for those males to actually avoid hostile actions from females. And then, using the same data in another paper called Multi-Relational Organization of Large-Scale Social Networks in an Online World, you observe that pronounced power law distributions from aggressive behaviors, but a lack of power laws for positive links. Could you break down these findings for us?
Yeah, this is something that was very unexpected. So if you look at networks of cooperation or networks of friendship or network of trade, which is generally seen as some positive type of interaction, then if you ask how likely is it that any randomly chosen person has X connections in that network, this is not a power law. Whereas when we look at interaction networks of enmity or aggression or attacking others, these are also networks. These show power laws. And what does that mean? That means that some or a big fraction of people has a lot of enemies, like really many. Or some people are seen as, I don't know, Stalins and Hitlers. Everyone hates them. And there's quite a fraction of these, and then there's a lot of people who have pretty many enemies, many more than you would ever have friends. So if you do something bad, many people react to that and mark you as an enemy. Whereas if you do something good, okay, no one really sees that as a special thing. That's expected, kind of. But it's really interesting that these kind of things show up really clearly. It's not like a curve being bent a little bit less. The aggressive networks are scale-free and the other ones are Poisson.
It is indeed very surprising. Were you expecting to find that when you started the research? No.
Not at all. Not at all.
Yeah. All right, let's jump now, and this will be quite a stretch from sociology to finance. You have another paper called "What is the minimal systemic risk in financial exposure networks?" And in that paper, you found that different structures of financial networks come with different risks. And from that, it follows that scaling up capital requirements might not be sufficient to prevent future systemic events. And instead, you may want to have what you called macro prudential rules. Again, could you please unpack this claim for us?
Yeah, so different networks come with different systemic risks. That's important. What is systemic risk? Systemic risk is the feature of a network system that you can have a little problem locally, and this problem may spread. In financial networks, that would be the default of one bank could bring other banks to the edge of default. They might be kicked over the edge, and then you could end up with a cascading event, like an avalanche going through the network and destroying the network. It's a little bit like if you have a sweater, and if you make a hole in it, if you have a good sweater, you can wash the sweater with the hole, and the hole stays the same size, more or less. That's a good network topology of your sweater. But if you have a cheap sweater, you burn a hole in it, and then every time you wash it, the hole gets bigger. So the difference of the sweaters is the network, is the way the thing is woven. In a similar way, if you restructure given financial networks in a tiny way, you can make these networks much more robust.
which is not a common approach in the sense that we tend to look at efficiency a lot, and regulation does a lot for efficiency, but maybe less for indeed making sure the networks are robust and can actually have a hole in the sweater and still survive being washed quite a few times.
Yeah.
You have another paper, and this will slowly lead us to part two of the conversation on the new forms of collaboration between the social and the natural sciences, in which you document the social phase transitions. And for example, you note that in physics, the triggers for these phases are well defined. So we know how water shifts from being liquid to ice to vapor. This is due to variables such as temperature, pressure, volume. But in social systems, what defines the collective state is less clear. So what did you discover in the space?
This is ongoing research, and it's super exciting. We're finding. So you are asking what could be temperature in a social system. So, and we say, couldn't it be, or we ask, couldn't it be that it's the number of communication partners that you have? Yeah, and what could be the phase of a social system? So there could be a homogeneous phase where you have a society with people that like each other and don't like each other, but you can reach every person through links that through positive links. And then there could be a different phase, a fragmented phase, where all people that like each other, they form little bubbles. They still like each other, but they hate all the others that are outside of their bubble, or they might not hate them, but they're highly suspicious. And what drives such a phase transition from a democratic society into a bubble society where democracy does no longer work? And we are finding more and more that the number of communication partners might play the role of temperature. So if you have more than a critical number of conversation partners, then you are entering, or you must enter, a bubble phase. Now, did the number of communication partners change in the last 20 years? Yes. Guess when? So 2008 is a critical year. That is when the smartphones start appearing, and when Facebook and this kind of social platforms start appearing.
Yeah, so in a sense, the social networks, it's not that they do not connect people, but they connect them to so that they can form those bubbles. Or I mean, it's not the purpose, but that's the end result. Okay, talking about those bubbles and connections, what's interesting is when the bubble may explode. And that leads me to economics, because you have, and this will be the final paper I want to explore for now, another one called Quantifying Firm Level Economic Systemic Risk from Nationwide Supply Networks. And in that one, you show that 0.035% of companies have extraordinary high economic systemic risk. And in fact, those companies could impact 23% of national economic production should any of them default, right? So this is one of those little bubble, or one company, a node in a network exploding, going away. And you explained that to avoid those hyperscaled issues, we may want to introduce supply chain redundancies and changes in the network topology. So again, now is your turn to unpack this paper for us.
So we had access, or we have access for a couple of countries, to value added tax payment data. So which company pays value added tax to another company? And from this, one can reconstruct the legal part of the economy. Again, this is networks, who ships what to whom. And if one company goes out of business, we can in a model that we have, a one-to-one agent-based model, can kick out any company that we want after another, and see how much does the GDP of our model economy go down. And that's our test quantity for how systemically relevant or important a company is. And then we find this 0.035% of companies If you kick those out, they would bring down the economy by 25% or 23%, which is a disaster. And if you look at these companies, who are they? Of course, it's the energy producers. If the atomic power plant of that country goes out of business, country goes down. If the big cement producers go down, okay, then that stops building industry, and that also will bring down the economy. So these are things that are expected. 50, 60, 70% of all the companies that we find with this super systemic risk, you would say, yes, of course, of course. I knew that before. But then you also find a couple of dozen other high systemic risk companies that you would never think of. So maybe a small family business. It's not size at all, but they are producing some special part that you might use to run a turbine in an atomic power plant. And if that product is not substitutable, if there's no other company in, I don't know, in Europe or in the world that produces the same thing, then this little tiny company that goes out of business might stop the giant, and then the giant brings down the economy again. That's the practical use for this, to not oversee some of the producers that are producing things that we really need. We never thought of it that we really need it, but we do. And this is getting more and more important in a more and more globalized and more efficient economy, where there shouldn't be 10 companies producing the same thing. There should only be one. That would be the most efficient thing. And of course, there shouldn't be, for several reasons. But this reason for not being substitutable anymore, this increases systemic risk drastically, and we were overlooking this a little bit in the last 3 decades, I guess, where we just saw the increase of efficiency and did not look at the reduction of resilience or robustness.
This is so relevant for merger control, because indeed, if you can justify efficiencies, then most likely the merger will go through, but at the costs, not always, but it could be at the cost of indeed the resilience of the supply chain. So it seems to me you may want to factor that in.
This is a cost that typically the public bears. In drastic event happens, the public bails out the banks in the financial system, or the public suffers by not having, I don't know, basic provisioning for a couple of months or something, or non-availability of medicine or any other thing. So these public costs are externalities, and in our economic system, if there is externalities, one could tax those, or one could enforce insurance premiums for creating these kind of risks. So if, as you say, if you have a merger that makes the thing more efficient, therefore one should do it. But if it also creates systemic risk, maybe there should be something like an insurance premium that they have to put in a basket, and in case something goes tremendously bad, at least the money is there, and they themselves pay for the damage and not the public.
This raises the question of institutional capacity to even see that there is such a risk, and then considering what are the options, indeed on the table. And to some degree, the economists working in institutional economics are well connected to the complexity economists. So I hope maybe they could team up to, make a point to others that there is something there.
And what is kind of nice is that we can show that there is no technical problem with this in doing that. So the bottleneck is legislation, is the political willingness to use this kind of data to get the public support for using this.
Yeah, this is huge. All right, let's move on to part 2. So now we take a step back a little bit, and I think what has become clear now to all of our listeners is that maybe they don't know that you are a trained physicist, but you are, and yet you've published, as we just covered, in economics, biology, sociology, and more. And again, this is me trying to put labels. We'll come back to that. But for now, I would like to know if you see yourself as a physicist using that foundation to explore other fields, or if you see yourself as a complexity scientist, if there is such a thing, or as a researcher that is just unbound by disciplinary labels.
I think I feel a little bit like a physicist. So this is like a goose that sees its first parent, just follows that, is primed, and I truly believe that most things happen for a reason. Can be stochastic, but there's a reason for things happening, and figuring out what triggers what has been done by physicists mostly. But of course, I'm not dealing with molecules. I'm not dealing with atoms. Many complex systems don't have conservation laws that makes physics so beautiful and so simple. I don't know what a complexity scientist is. this is this is a label that's new, and
You
people.
are.
I
I
am,
mean,
yeah.
if
Maybe.
anyone, yeah.
Sometimes I think that many of our of complex systems have networks that evolve over time, and these networks are the forces between the components that make up the system. And the networks change the components, and the components then feed back and change the networks of networks. Of course, I have no insight into this. Is what I call a complex system. In physics, the forces never change, and the forces are completely different in scale. Gravitation and the strong nuclear force are, I think, 40 or 42 orders of magnitude different in strength. So if you're looking at one phenomenon, you always have one force. If you're looking at the complex system, you have many forces acting at the same time, like the multiplex networks that you mentioned before. So I think I see myself as someone who likes to identify problems, and my technical skills are in the dynamics of into economics and biology and sociology and physics. Of course, not this interaction part, and how forces change while the system is evolving. That's something I'm fascinated with.
But so let me ask a follow-up question, because as you just explained with the multiplex networks, it might be that a force driving some of the agents may be, I don't know, economic at some point, and then the very same agent will be driven by something different, maybe in a week or two from now, right? They will be driven by politics. So I guess this would be a difference from what I understand compared to physics and indeed the law that would drive, the system consistently. So I guess my question is this: when you apply physics-based approach to complexity, do you see a limit sometime? Do you feel that the methodology is limited because indeed the dynamics of all complex system cannot necessarily be understood through the lens of physics, or do you see a way to accommodate for those complexities?
So in physics, we had this general recipe that we could always fall back to, right? Describe a system. If you don't know how, find the differential equation, solve it, show that it is similar to the experiment that you do, and harvest all the fame or start new. This you could do because you can fix boundary conditions in physics. Complex systems, you cannot fix these boundary conditions. So we have to find a new way of describing a system, but not losing the scientific method. So, in this way of describing is very often through agent-based models. Rebuild the system, show that it does more or less the same thing as we see in reality. Find the causes of what drives what, and then, in the best of all cases, you can find these things back in reality, and then you have maybe understood something. If you have these agent-based models, you're describing things in an algorithmic way and not in an analytic way. So Brian Arthur pointed me to that difference. But the scientific method is the same. We can still make predictions, can be falsified in exactly the same way. And it's also not new. If someone 100 years ago would describe a steam engine, they would also not write down differential equations, but they would give you an algorithm. This piston is pushed by the steam here, then it opens a valve, then the steam goes the other direction, pushes it back. And that's an algorithmic way of describing things.
So, on that, Brian Arthur that you just mentioned has a very elegant paper entitled Economics in Nouns and Verbs, in which indeed he makes a point that seeing the economy through algorithm enables you to see actions and movement as opposed to just using algebra, which by default is one side equals the other, which is very fixed. And his
Yes.
approach to ABM actually reminds me of the way you are using it, because Brian and yourself are to explore the full potential of agent-based modeling, fine-tuning your agent-based models with real data, quote unquote, right? So from what you see in the real space. My question is this: where do you think that real data augmented ABM, to call it this way, has already most advanced scientific understanding?
I don't know. I don't know. I'm too ignorant in other fields, but
But let me ask then about your work. Where do you think it has been the most promising in where you used it?
I think in supply chain models, in rebuilding the economy in a computer with as many agents as there are companies in a country, so hundreds of thousands of agents. Everything that is shipped between them is part of the model. Then we try to learn with whatever machine learning or statistics techniques. How can we explain the turnover of our economy? Companies that you see today will not be there in a year. And 60%, 50, 60% of all the links will be new next year. And yet the whole thing is tremendously stable, producing the same stuff over decades with not so much change.
But even within the firms, I've learned recently that companies such as Netflix and Spotify will lose more than half of their subscribers on a yearly basis and will actually regain another half. So it looks like they have the same amount of subscribers, right?
Yes, yes, but
But
it's new. It's
yeah,
a new set of people.
and I think Netflix actually loses 100% of their subscribers, I think, on a yearly basis. So the turnover is huge.
Yeah, rightly so. They've lost me too.
But maybe in a couple of years, you'll come back to it for a couple months just to catch up, with a couple
Yeah.
of TV shows, and then they lose you. All right, we are nearing toward the end, and I want to ask something which is slightly on the edge and different, because you have a publication about peer review,
Uh,
what you call peer review in the world with rational scientists, and you present a strong critique of the peer review system. Now, for someone running a journal, what alternative approach would you suggest for improving scientific quality?
so the suggestion we made there in this paper was stop all the reviewing work and throw a dice. That is beneficial to the scientific community. Why? We built an agent-based model. We have a community of N scientists. Every scientist produces one paper per year. And this paper is submitted to two randomly chosen scientists. If both of them like it, the paper is published. If one of them doesn't like it, the other one likes it, you throw a coin, and with 50-50 chance it's accepted. And if both dislike it, it's rejected. Every author has a quality level, and every author can only produce papers that are more or less at this level. Then we run the system and observe if the referees are doing what referees should do: pick good papers, reject bad papers. The system works fantastic. But if we start introducing referees to the refereeing pool that have own interests, then the thing starts to change. And we call this a rational scientist. What is a rational scientist? A rational scientist accepts papers that are worse than his own or her own. As a rational scientist, if I see a brilliant paper, I have an incentive to not have it published. Then the other guy gets the fame and not me. If you introduce 5% or 10% of these rational under quotation marks scientists, then or selfish scientists, that's what they are. System no longer selects good papers, but it focuses on the mainstream. and the variance of quality is shrinking. So you're getting the mainstream stuff and no more fluctuations, good or bad, upward or downward. The mainstream doesn't bring us forward. What brings us forward is the fluctuations. Papers no one thought of, really crazy in the beginning. These we are ruling out, and therefore we said if we just roll the dice and accept papers by flipping a coin, we could maintain this big variance of quality, not throwing out the good ones.
Are you peer reviewing papers? Are you accepting those invitations?
Yeah, I'm getting maybe one invitation per day on average. I'm not taking all. I'm trying to be a fair player. I'm trying to do twice as many reviews as I publish papers.
Okay, let me ask a final question. Can you tell us more about the Complexity Science Hub Vienna, and more specifically, what is the vision and how does it complement with the Santa Fe Institute, where you also serve as an external professor?
The mission is to use the bigger and bigger data sets that become available to us immediately for improving our society, like green transition, fragmentation of society, crypto crime, unfairness in algorithms, etc. For no commercial reasons. That's important. How are we different from the Santa Fe Institute? We wanted to be the baby sister of the Santa Fe Institute in Europe. Now we found ourselves much more applied than researchers at the typically working at the Santa Fe Institute. Is that good or bad? I don't know. Looking back into the history of science, you could make both points. Say science always solved problems, so it has to be applied. Or you can say no one of the big thinkers really tried to solve a real world problem. That's not really true. I personally think most people had a really clear practical problem. If it's Einstein or if it's Copernicus or if it's Kepler, they all had practical problems they wanted to solve. But if you go more into detail, then of course you will find situations where they are thinking purely without any incentives to solve anything. So
I'm reminded, we mentioned Brian Arthur quite a few times. A story he tells is that when he was in charge of the first group doing complexity economics, he was asked to come up with something groundbreaking, right? But it was very much for even the sake of it. So it was not applied. Indeed, this was looking at the very theoretical part of it, which we all love, I guess, as scientists.
yes,
But we
yes.
also like to see impact on the real world. I mean, how cool is that? So
Yes.
yeah, so complementary very much. Yeah.
So we observe this in young collaborators that we have at the Complexity Science Hub. If from time to time they can speak with the minister and show a potential solution to a problem to decision makers, and then sometimes are listened to, and sometimes something really happens by changing a law or something. This is so motivating, and I think it's part of the attraction to be at the Complexity Science Hub.
So it's all about connections. That would be a good way to end the conversation. Thank you so very much. It was such a pleasure for me to have an excuse to dive into most of your papers, not all, but the ones that I could comprehend. So thank you for that, for leading the Complexity Science Hub. And on that, to you and to everyone out there, take care of yourself. And if you can, someone else too. Bye-bye.
Bye.